All right, so we're going to start this video by looking at the beginning of chapter 10. And chapter 10 is all about acids and bases. Now, quick disclaimer about this particular chapter. The textbook is going to go into acids and bases in a lot greater detail than what we are. In fact, we're going to skip a couple of sections in the textbook related to equilibrium pretty much entirely. So just be careful, and when you go into the reading assignments, make sure that you recognize that some of the sections have been omitted and that we may not necessarily even cover everything that's in a given section. So that's being said, let's get into what we do need to know about acids and bases as far as our own general understanding and knowledge is concerned. So we're going to start off, first of all, just by kind of defining what acids and bases are. And so this is section 1 in the textbook here. And so the term acid comes from a Latin word, acidus, which means sour. And the terminology here comes to one of the real defining characteristics of acids, which is that acids taste sour. And so when you look at citrus fruits, most citrus fruits, in fact, all citrus fruits, contain a combination of several different acids. Citric acid being the one that is primarily associated with the sour, bitter flavor that comes with most of these compounds. But we also get ascorbic acid, vitamin C, in a lot of these as well. When we define acids, there are a number of different definitions that we can use. Probably the most common definition is the Arrhenius definition. The Arrhenius definition gives acids and identifies them based upon the presence of hydrogen. So when we describe acids as being a molecule that has a hydrogen in the front of the formula, that's the Arrhenius definition. And the definition goes on to kind of further take on this idea that the hydrogen itself is going to be produced when that acid dissolves in water. So we take something like hydrogen chloride, which exists as a gas outside of water, put it into the water, and it dissolves and creates hydrogen ions and chloride ions. The hydrogen ions are what make it an acid. The chloride ions, together with the hydrogen ions, give this strong electrolyte characteristic because, again, we're seeing complete break apart of the molecule into ions. And we're also seeing that this process happens when it dissolves. So if we go back to what we were talking about in chapter 9 about electrolytes, what we will see is that these are strong electrolytes because we are getting the presence of ions and we're getting the complete breakdown of this molecule into ions as opposed to a partial breakdown. Now, some other characteristics of acids in general, not just Arrhenius acids, they have a sour flavor. They will also turn blue litmus to red. And red can be kind of a pinkish color as well, depending upon what kind of litmus it is, how old it is. And acids are known to corrode some metals, but not all. This is a list of common acids, and the majority of the common acids are acids that we would find, just laying around the house or in a more laboratory setting, especially. So hydrochloric acid is an acid that we can find in the house, comes in a variety of different forms. Different kinds of cleaning agents might contain hydrochloric acid in it. Nitric acid, sulfuric acid, these tend to be acids that we find in the laboratory. Carbonic acid, this is what happens when carbon dioxide dissolves in water. So this is naturally found in carbonated beverages. It also randomly decomposes in carbonated beverages to give them their fizz, which is why you'll have carbonic acid put into beverages, knowing that it'll basically break down into carbon dioxide upon usage. Acetic acid can be found in vinegars. Phosphoric acid is sometimes found in certain types of sodas, especially colas. And some of these other ones can be found in some different kinds of oxidizing situations. So all of these are common acids. They all are Arrhenius acids. And again, we can pick them out because if you look at the chemical formulas, all of those chemical formulas start with H. And that's what makes them Arrhenius acids. Let's compare that with bases. Arrhenius bases, by definition, are going to be compounds that look like salts. So they're going to be, metal, non-metal kinds of ionic compounds, but they have hydroxide groups, OHs, at the end. And so this is what is going to kind of differentiate bases from what we saw in our organic units as alcohols or acids. That OH group, or that OH with the carbonyl group that we saw in the organic unit, we aren't going to see that here because these are ionic compounds, not molecular compounds. So let's put that note in there. Arrhenius bases will form hydroxides in water. That is one thing that they do. They have a bitter kind of flavor to them. They can also seem kind of chalky. And like the Arrhenius acids, they are going to be electrolytes because when they dissolve into water, they will break apart into ions. The ions will be the metal ion, in this case sodium, as well as the hydroxide ion. Interesting, bases feel soapy and slippery. Since we've talked about saponification reactions, we now can kind of understand that. Your fingertips have oils on them, have little bits of fatty acid kind of tissue on them. And so when that hydroxide hits that, it creates a saponification reaction right on your fingertips. And that's what's going to give that soapy, slippery kind of consistency. Now, you're going to want to wash that off really quickly because prolonged exposure to hydroxides will actually drastically change your skin and can actually lead to scarring. But if you just touch it for a couple of seconds and then wash it off, you'll get that soapy, slippery kind of feeling to them without actually damaging your skin. As far as indicators are concerned, bases will turn indicator paper blue. That is litmus paper. They'll also turn phenolphthalein indicator to pink, or kind of a magenta color. So those are kind of your basic definitions of acids and bases from the Arrhenius standpoint. Again, the Arrhenius standpoint is one that we can look at based solely on the chemical formula and not on the reactivity. So when we look at chemical formula standpoint, hydrogens are ionic compounds that have hydrogen at the beginning. That's what an acid is. Bases are ionic looking compounds that have hydroxide at the beginning, or excuse me, hydroxide at the end. So we either have hydrogen at the beginning, acid, or hydroxide at the end, base. Now, there is another definition of acids and bases. It's called the Bronsted-Lowry definition. Now, the Bronsted-Lowry definition of acids and bases is a little bit more complicated. And we're going to make a note here. The note we're going to make is basing it on reactivity and not formula. So in the Bronsted-Lowry definitions, which are based on reactivity, not formula, what we're looking at is primarily what happens to H+. Acids are substances that when they react will give away H+ ions. Bases are substances that will accept H+ ions. The net result that will happen in acids is usually the formation of this hydronium ion if we're dealing with water. So what's happening is this hydrogen on the HCl leaves the HCl, attaches itself to the water. And so as a result, we would identify this as a proton donor, a hydrogen donor. And that makes the hydrogen chloride an acid. And the water, which has accepted that hydrogen ion, is now considered a base. And the net result is that we get the hydronium ion and the chloride ion. Here are the two ions that make up our electrolyte. On the flip side, ammonia can act as a base by taking one of the hydrogens off of water. And so as an acceptor of that hydrogen ion, it is going to be acting as a base. It is a proton acceptor. And the acid in this case would be water, the proton donor. Now, one thing that you should notice is that with these Bronsted bases and with these Bronsted acids, we are getting essentially the same things as what our Arrhenius definitions were doing. When we talk about the reactions of these acids and bases with water, what we will see is that bases give us hydroxides and acids give us hydrogens in the form of hydronium. So from that standpoint, the Arrhenius definitions and the Bronsted definitions do work together, and they do talk about the same things. In fact, every single acid that is identified as a Arrhenius acid is also a Bronsted-Lowry acid. And every base that fits under the Arrhenius definition also fits in as a base in the Bronsted-Lowry definition. The only difference is, instead of, again, just identifying things based on formula, we're identifying them based on what they do, how they react with other stuff. And so what this opens up as an opportunity is the ability to have acid-base kinds of reactions and characteristics that don't have to involve water. The Arrhenius definitions have to involve water. But with the Bronsted-Lowry definitions, we can see acid-base character evolving, and water doesn't have to be an active participant in the reaction itself. It can be a side participant as just merely solvent and not as reactant. So comparing these kinds of things from a variety of different standpoints. Again, the Arrhenius definition for acids and bases: acids produce hydrogens and bases produce hydroxides. In the Bronsted-Lowry definition, acids donate hydrogens and bases accept hydrogens. Regardless of whether we are dealing with acid or base, they are going to produce electrolytes. Now, there is going to be a difference. We will talk about this in the next section, but there is going to be a difference in terms of some of these acids and bases will produce strong electrolytes and some will produce weak electrolytes. That gets into a discussion of acid and base strength. But what we do need to understand is that they all will behave as electrolytes. And that is important to understand. That is important to recognize. Now, from a taste standpoint, acids taste sour, bases taste kind of bitter and chalky. You can kind of think about, what does an antacid taste like? For the most part, they kind of taste, they taste bitter. They kind of have a chalky consistency. Acids can sting on your skin. Bases can kind of feel soapy and slippery, at least at first. Over time, they will begin to sting and redden the skin and hurt. Acids kind of give you that right away. Litmus paper will appear red in acid, but blue in base. Phenolphthalein, which is a very common acid-base indicator in the liquid phase, appears colorless in acid, but pink in base. And acids and bases do neutralize each other. And when we get into not this lecture, but the next lecture, we'll talk more about those reactions that take place between acids and bases. But for now, let's just kind of review a couple of the concepts that we just went into. So for this question, what is the Bronsted-Lowry acid and base in each case? Now, to answer that question, we have to look at the difference between reactants and products. And the thing to do is to look for similar pairs of items. What I mean by that is I can look here and see, okay, HNO3, well, on the product side, the product that is closest to HNO3 is NO3 minus. And on the flip, the water, its closest cousin is this H3O plus. Now, to try to figure out what happened, I need to look at the differences between these two. So for the water, we can see that we went from H2O to H3O plus. We added a hydrogen and we added a +1 charge. Adding a H plus proton acceptance is a base quality. What happened between the nitric acid and the nitrate? HNO3 versus NO3 minus. Well, in that process, we lost a hydrogen and we lost a positive charge. That's why this one's now negative. Loss of a proton, loss of an H plus, is an acid characteristic. And so the HNO3 is the acid. Let's look at another set of circumstances. HF reacts with water to make H3O plus and F minus. Once again, it's in our best interest to try to pair together the things that are the most alike and see how they change. And if we can do that, like so, it'll help us to understand better what was happening here. So the H2O became H3O plus again. Same principle. I added an H plus to go from water to hydronium. That's a base characteristic. And for HF, HF went to F minus. It lost a hydrogen along the way. That is an acid characteristic. So HF is an acid. Let's take a look at some more review. Identify each characteristic as that of an acid or of a base. Well, for this, we just got to go back to that chart. So which of these has a sour taste? Well, that would be the acid. So that's A. Which of these produces hydroxides? Well, by definition, according to the Arrhenius definition at least, that would be a base behavior. So that's B. Which one tastes chalky? Well, acids taste sour. B, bases must be the ones that are chalky. Which one is an electrolyte? Trick question. It's both. Both are electrolytes. Both produce ions in solution. Which one produces H plus? Well, hydroxides are indicators of base. H pluses being produced in aqueous solution. That is an Arrhenius definition. So that's A for acid. So there's one more thing that we want to talk about here in this first kind of introductory coverage of this material, and that is acid and base strength. So this is section 10-3. Now here in 10-3, we're talking about, well, what is the difference between a strong acid and a strong base? What is the difference between a strong acid and a weak acid? And it comes back down to something that we talked about when we talked about electrolytes, the idea of partial dissociation. So the thing that makes a weak electrolyte weak is the fact that those molecules only break apart slightly when they get dissolved in the water. They all dissolve, but not all of them break apart. And so by comparison, we see strong acids will ionize completely. So all of the HCl's get turned into H3O pluses and chloride ions. And so this is what gives us a strong electrolyte as a result. Because as a strong electrolyte, we would have a lot of ions present. And if all of these molecules are turning into ions, then yeah, we're going to have lots of ions present, because this reaction is only one way. It only goes from reactant to product. Weak acids, on the other hand, will only slightly dissociate. And so they form a few ions. The fact that they form any ions makes them an electrolyte. But the fact that they only form a few means that it is a weak electrolyte. And so in a weak electrolyte like carbonic acid here, we will get some conversion to the hydronium ion and the bicarbonate ion, but the majority of those ions is staying over here. On this side of the reaction. So most of the molecules are staying as molecules and are not breaking apart. Some are, and because some are breaking apart, we do have electrolyte character. It will conduct electricity, but it will do so quite weakly. From a molecular standpoint, again, we can see the differences, the HCl here, the strong acid. We see all of these ions present all over the place here. The acetic acid here, we see the majority of the molecules are staying completely together. So here's an example of one together, 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 together. So we have 8 molecules that stay together and 1 molecule that did not stay together. It ionized. So that's a little bit better than 5%, but this is also an incomplete picture. The net result here, though, we can clearly see that the majority of the molecules stayed together. Only a couple of them broke apart. So will this conduct electricity? Absolutely. Will it conduct electricity as well as the hydrochloric acid? No way. Not even close. So how do I identify a strong acid? How do I identify a strong base? Well, these are interesting questions, and unfortunately for us, there's really no way of knowing other than to just simply memorize them. So there are 6 common strong acids. They are here on the slide here in table 10-3. Hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric acids. Those are the 6 that you need to know. If it's not on this list and we can identify it as an acid, then we must know that it is a weak acid. So these 6 are strong electrolytes. Everything else is a weak electrolyte. Now for strong bases, it's a little bit easier to see. Your strong bases are hydroxide salts, formed from the metals in group 1A and group 2A. So these are your alkali metals and your alkaline earth metals. So these would be things like lithium, sodium, potassium, calcium, strontium, barium. Now there are other examples in those, but these are the most common ones. And some of them even have, familiar names to them. Lye, potash. They all have in common the fact that they all completely break apart. They all dissociate. So we will always get 100% dissociation from these strong bases, which means they will be strong electrolytes. The important note here if it is not one of these strong bases, then it's going to be a weak base. So this would include anything like aluminum hydroxide, or one of the transition metal hydroxides like iron 3 hydroxide or copper 2 hydroxide, which, yes, they have basic characteristics if we can get them to dissolve in water. Problem is, most of them we can't get to dissolve in water, and if we could, it would only dissociate weakly. And so as a result, they don't tend to be in use very often. Probably the most common weak base that's out there is ammonia. Ammonia or ammonium hydroxide, when it dissolves in water, that is something that is a little bit more familiar. And if you're looking at household products like window cleaner usually have ammonia in it, or at least some of them do. And it's a weak base. The ammonia does dissolve. It dissolves very, very well in water, but it does not dissociate particularly well. And so this is where I'm going to stop the reading, stop us for today. In our next lecture, we will go through the rest of chapter 10, at least the relevant parts to us. And in that, we will discuss the pH scale, which is a way that we can quantify just how acidic or basic a solution is. And we'll also get into some reactions of acids and bases. And some of the places where we can see them kind of in most common use for us, before concluding with a really interesting application of acids and bases, and getting acids and bases to regulate pH very, very, very well, which is what happens in our body systems through the use of what are called buffers. So that's what's coming up on the horizon. If you have any questions, please feel free to reach out to me. But until then, I will see you next time.